So the next speaker is Thomas Kozikowski from another partner in Organic Ventures. Thomas is currently field application chemist, has 17 years of experience. And when I read his bio, I was amazed. He has done every single thing you could possibly imagine to do at the top manufacturing company for reference materials, which is an Organic Ventures are. I have a very long history. I won't take Thomas' time. I know personally the owner who started, Paul Gates, we started in 1997. Came actually when I was an application chemist at Spectral. And Spectral was a very small player in ICP-MS, but there was some chemistry between us. Anyway, he ended up buying the instrument, and I ended up fixing it, going there to Organic Ventures Lakewood, New Jersey. So that's how the relationship started. But back to Thomas. So he has done quality control, technical support, stability, and homogeneity of inorganic metal standards. His experience covers many areas, including reagent synthesis, purification, trace metal analysis using ICP, transpiration studies, and container cleanliness. Thomas has a bachelor degree in chemistry and also bachelor in forensic science from Virginia Commonwealth. So don't miss it.
Thank you, Sergey. Good morning, everyone. As he mentioned, I've been with IV for a really long time. So I've worked for Dr. Paul Gaines and Dr. Brian Alexander. They, started the trace metals and purity testing of standards a long time ago, and I kind of took that from them and made it into what it is today. But we've been doing that method for, a long time. I want to say 2012. And we really haven't changed that method. Every time we look at it, it's like, I don't really want to change this part of the method. It's working great. It's a robust method. We do a standard edition. It's matrix matched. But every once in a while, some of our vendors will come at us and be like, hey, try this nebulizer or try this tubing. And we gave it a shot. So I've been here to talk about one of those suggestions from Sergey. So our key focus, we're going to talk about our current method that we use for trace metals. So if you look at our single element standard, some of our multis, you'll see a trace metals profile. We do that by OES and mass spec and combine that data. But we're going to go into the future needs and then go over our OptiMist Ultimate Nebulizer trial and kind of show the performance report results from those and also a data comparison of two different materials, and finish out with some washout observations. So our current trace metals method for the mass spec, we run the major element that we're looking at 100 ppm. So it might be like 120,000 ppm calcium or maybe 100,000 copper. We'll dilute that down to 100 and we will spike it with two different spikes. So we'll do one with a 4 ppb spike of 65 elements in nitric and trace HF. And we'll also do a 4 ppb spike of 12 elements in HCl and HF. You'll note from this chart that 7 of those elements are actually in both for interference mitigation reasons and chemical stability. So, with vanadium, we have chloride and argon issues. Palladium is just sticky and kind of a pain in the middle of the mass range. So we do check that on both. And arsenic, selenium are also chloride-based interferences. The sequence itself will run 3 blanks at the beginning of the run, and we kind of look out for a little bit of washout from the previous run maybe, but we'll take the standard deviation of those blanks for detection limit calculations. Then we'll run the sample plus spike, and then we'll run 3 additional blanks to monitor washout and make sure everything is okay before we proceed to the next analysis. So we are routinely running this on our older Thermo X Series 2. So it's still plugging along. I was really happy to see in some of the short courses this week that I took that they're still out there. We're still using ours. Really nothing wrong with it. We are using an OptiMist nebulizer on this, so that's the one pictured here. It's made out of PFA material. It's a concentric nebulizer, but it's HF resistant. As you know, we don't shy away from HF in our lab. Some of these elements require it. So this really helps us get good purity with our runs. We are also running a syringe drug assist system for sample delivery. So it's pushing the sample with the syringe instead of the peri-pump, and this helps with reproducibility. But also because there is a sample loop, we don't have the sample touching PVC pump tubing, and washout is much less of a concern. So we really love that system, but you are limited to the amount of sample time in the plasma. We are using collision cell technology. We've got the 8% hydrogen and helium running in non-KED mode. And we do scan masses from 6 to 238, including mass 40 for calcium, 56 for iron, and 80 for selenium. That gas works really well for those, and we get pretty good detection limits. We do try to limit the TDS, of course, to 100 ppm for most analyses, but we ensure we never go over 2,000 ppm. One thing to note, if you're not familiar with the X Series 2, it does not have the lens shift technology or the right angle ion path. So we do have to be very careful about turning off the masses that are really high. So if we're running that 100 ppm calcium, we turn off mass 40. If we run thorium, we turn off 232, so that we preserve the life of the detector. So this is what the sample entry system looks like on our X Series. We are running nickel cones, quartz torch, a sapphire injector, quartz spray chamber. Even though we do have HF in our standards, it's trace low level, it doesn't eat the spray chamber, but we do obviously have issues with silicon. So when we want to do silicon off of the OES and need to use mass spec results, things get a little dicey. Of course, I mentioned we're using an OptiMist nebulizer and a 1% nitrate carrier solution, so that's always pushing through as the valve switches from positions from loading and injecting sample. So we do have some future needs for this method. We've been doing it for a long time, but we are coming into the next generation of mass spec technology, so we are going to be getting a triple quad mass spec soon, which we're really excited about. Also have the capability of doing argon dilution with that. Our backup instrument does have argon dilution capabilities, so every once in a while we can run that with this trace metals method. But we want to start doing more with brine solutions. We get a lot of requests for that, where you need to know the trace levels in that high salt matrix. We need to make sure we have a nebulizer that can support that. So the OptiMist is probably not the best option for that. It could be prone to clogging. As you mentioned earlier, we don't want that. But also we're looking at expanding our offering to contract testing. We're really good at trace metals analysis, so we do want to bring that to the community. So we want to be able to do high concentrations with low detection limit requirements of other elements. So again, prevent the nebulizer clogs when running those higher samples. To put it in reference, the OptiMist tolerates about 75 micrometers, particulate, whereas the OptiMist Ultimate has a sample width of 1 millimeter. So we really don't want a filtered solution, so every once in a while you get that speck of dust. Filtered solution might introduce contamination, and we're trying to get the lowest detection limits possible. So our OptiMist Ultimate trial. So we did try 2 different samples without changing settings. So we did some performance report tests and then also real world samples that we test. So the OptiMist Ultimate is meant for an OES. I will put that. When I mentioned to Sergey, oh, hey, I want to try this in the mass spec, he's like, I don't know if this will work. But we tried it. We just couldn't do the flow rate that it's designed for. So keep in mind, this is designed to be run at 2 mils per minute, whereas the OptiMist that we have is 0.4 mils per minute. And we've finally tuned this method to use a sample loop. So if you think about it, we really can't run this unless we get either a bigger sample loop or cut down on the number of replicates. So that's one of those things we'd have to fine tune, and timing matters. And it's a really long run. We scan all the masses, we do 6 replicates of each. It takes a long time. So we also moving back, we retuned the OptiMist Ultimate to see what it would look like and see if we can get RSDs better and counts to be similar. I will mention that we did do a higher sample rate for the Spike 2 solution that we do. It only has 12 elements, so that's a faster run, and we did get some data for that. So looking at performance report results, we did the OptiMist first, of course. We just took one of our runs, got really good data. This is actually a really good day. So our Thermo likes to look at 7 lithium, 115 indium, and 238 iridium. So I've got the counts and the RSDs listed. You'll see for that first set of columns, 80,000 counts for lithium. The spec is 60, so we're well above what we need to be. With indium, it's supposed to be above 400,000. We're at 800,000, and then iridium is supposed to be 800,000, and we're in the millions. So these really good day. The RSDs their spec is 2%, and all of these are well below 1. So this is all acceptable data. And then of course the cerium oxide ratio is the one I care about the most, but we also look at doubly charged. Those are supposed to be below 2%. We're at 1.5. Everything looks fine. We move over to the OptiMist Ultimate. This is without retuning. All we did was take the nebulizer out, put the new one in, and ran the performance reports. And you'll see the data, they're the same. Same number of counts, RSDs are in the same ballpark. Was really shocked that we didn't change any other settings, and it looks fine. And then when we did retune to make sure the oxide ratios could be as optimal as possible, you'll see that the counts are in the same ballpark. The oxide ratio did go down slightly, so we're at 1.26%. But across the board, I have those highlighted in green. The RSDs did lower quite a bit, and I'm happy if they're below 2%, and these are in the ballpark of 0.5%. So we're really excited to see this. Now, with the real-world data, we tried trace metals for our hydrogen peroxide starting material. So some of our materials do need to be reacted with peroxide in order to go into solution. So we need to make sure when we, acquire that, it's an acceptable purity so that our final product is not tainted in any way. So we used the 30% peroxide. We diluted it down to 3% for this run, and of course spiked with the 4 ppb spikes of all those elements. And the RSDs, the average across the board ended up being about 2.7%. On both nebulizers. I like to look at the mid-mass range of the rare earths, so from 138 barium to 181 tantalum, and you'll see that the RSDs there are really good. They're really high abundances, high mass elements. It's just a really good region to see how well your method's performing, and these are well below 2%. And the average counts I've mentioned there, they're in the same ballpark. We also did this for 100 ppm thorium. It's a material we're looking at right now to source. And the average RSDs were a little bit higher, not really that bad. But again, these are really similar results. I'd say if you threw statistics at these, you're not going to see a difference. So that's good news for a candidate nebulizer. And then our detection limit comparison. So with Spike 2, I was able to increase the flow rate per Sergey's recommendation. Couldn't go all the way to 2 mils per minute, so we tried 1 mil per minute, and the syringe plunged almost all the way to the top. If it had gone all the way to the top, it would have aired out the run and would have had to rerun it with slightly different settings. But we were successful with this. So the OptiMist, you'll see, these are detection limits in ppb actually for the undiluted solution. So this thorium is really at 10,000 ppm, and those are the detection limits for that solution. So across the board, really good for these elements. So ruthenium, palladium, osmium, iridium, gold, and mercury. You couldn't ask for better. You'll see here that the counts, I mentioned the counts, but I didn't display them. With the higher flow rate, as you would expect, the counts increased by a factor of 2. So that helps with the detection limits, of course. But across the board, really, really good detection limits. when you do have this at the 100 ppm level, what you're actually seeing is all of these detection limits are below 10 parts per trillion. And our method, if it's less than 1 part per trillion, it does round up to 1, because that's kind of what we are confident in reporting on our C of A's, so that you don't get a false sense of security with some of these, like, oh, we saw a little bit extra. Yeah, there's environmental factors at play. Now, the last thing is washout. So, of course, we always have to do our due diligence and make sure things are washing out before we run the next run. And so I picked on these elements. These are the worst in play. Tungsten, osmium, gold, bismuth. Bismuth always concerns me because we like to use that as an internal standard. It's actually a sticky element, so you do have to be careful. But these are the raw counts of those blanks that I mentioned. So the 3 at the beginning of the run and the 3 at the end of the run. And you see the counts are really good. The only one to note that might have still been washing out in the first set was the gold, which is very expected. We run a 1% nitric acid carrier solution. So when the valve switches back and forth, some of that gold will see the nitric and it'll start sticking to the plastic. If we were to use HCl, it would have better washout, of course. But 300 counts is nothing to complain about when 4 ppb is in the hundreds of thousands. But of course, after we run that 4 ppb spike and we run blanks 4, 5, and 6, we expect to always see counts here. With old PVC pump tubing, this would be in the 20,000 region. Of course, with our assist sample loop, 1,500 counts, not bad. I want to point out that osmium. I'm not sure what happened there, but there might be something there. Osmium didn't seem to stick around with this nebulizer. So we're gonna have to run this a few more times and make sure we know what's happening here, but that's encouraging. So osmium, as you know, as soon as you throw nitric acid in it sticks to every plastic you can think of. It takes a while to wash out. So we're gonna look at that as we continue to study. But keep in mind the OptiMist is made of a PFA plastic, whereas the OptiMist Ultimate is made of the Ultim, which is a polyether imide. So in summary, this nebulizer works fine for mass spec. It's designed for OES. It's designed for higher TDS samples. As we start running brine solutions, we use argon dilution. We can run things higher on our mass specs to chase those detection limits, but we need to make sure we have a nebulizer that does not clog. So I think this is definitely something to look at. Performs well, but it's lower than desired flow rate of 0.4 instead of the 2. We got similar counts, similar RSDs, and good detection limits. And the washout issues for the sticky elements were not any different with these inert plastics. So I would say this is an excellent candidate for running higher TDS samples by mass spec with that argon dilution. So with that, does anybody have any questions?
So the osmium is getting hidden in the nebulizer, so we can collect it.
Yes.
I had forgotten the context now, but earlier in your talk, you mentioned something about, I forgot the context now, but earlier in the talk, you mentioned something about palladium being sticky in a multi-element flow of your standards. I wondered, knowing of course that sometimes if you fix one problem, you cause another. I was wondering if you thought of adding more HCl to coordinate the palladium and hurry it through to eliminate the memory effect, or would adding HCl cause other problems if you'd rather have that?
Absolutely. So one of the observations we've made over the years is palladium is actually very similar to mercury. So if you run that with only nitric acid, you will have some memory effects, and it is easier to wash out with HCl, absolutely. But of course, if you have HCl in your matrix, you will have issues with argon chloride interferences, oxide interferences. So we have issues measuring arsenic and selenium, which are already not very abundant. So we put it in both solutions to make sure that we can have the capability of getting as low detection limits as possible for those. But yes, HCl is definitely the way to go with palladium. Any others? All right, well, thank you very much. I'll turn it back to Sergey.